Hi students, in last class I explained how to find out bond order for different ions. Okay, so now I'll explain that valence bond theory. So valence bond theory is proposed by London and Hitler and expanded by Pauling and Slater. So majorly it explains the directional nature of covalent bond. Means here, according to this, covalent bond is formed by overlapping of two orbitals having unpaired electrons of two different atoms. Okay, so two atoms when contain unpaired electrons in its valence shell, then those atomic orbitals are overlapped with each other. By this overlapping, a covalent bond is formed. Okay, the greater the extent of overlapping, the stronger bond is formed. Therefore, the order of overlapping is in this way. That is of PP bond is strong, then SB bond, then SS bond. Means PP overlapping is greater than SP overlapping than SS overlapping. In suppose if you take AB molecule, in this AB molecule, two nuclei are present that are Na and Nb and electrons are represented as Ea and Eb. In between of this nuclei and electron, which type of forces are occurred? That are attractive forces and repulsive forces. So attractive forces always present in between opposite charged particles. Okay. So therefore, totally four types of attractive forces are observed in this. So that are NaEA, nucleus of A atom and electron of A atom. Na and Eb, nucleus of A atom and electron of B atom. Again, nucleus of B atom, electron of B atom. Nucleus of B atom, electron of A atom. Okay. So these are the attractive forces. So totally four types of attractive forces are occur. And next, repulsive forces. So generally repulsive forces are occurred in between similar charged particles. So therefore, one type of repulsive forces is Na and Nb, other type is Ea and Eb. So repulsive forces are two types only. And based on the direction of overlapping of atomic orbitals, two types of covalent bonds are formed, that are sigma and pi. Okay, I explained this sigma and pi bonds in last class only. And next, according to this overlapping of orbitals are three types. Okay, so first, see here, based on the direction of overlapping, means if the overlapping is in straight direction, then a sigma bond is formed. Otherwise, if it is in partial direction, then a pi bond is formed. Okay, and this overlapping of orbitals are always explained in three types. Okay, overlapping of orbitals are explained in three types. What are they? One is positive or in phase. Second one is negative or in phase. Third one is zero or out phase overlapping. Now, see here, positive or in phase overlap means first and second are possible overlapping, but third one is not possible overlapping. So in positive overlap purpose, see here two positive charge of orbitals are overlapped with each other, and here also same like that. Here they indicated pz orbitals, here pz and s orbital, and here px and px orbital, py and py orbital. Okay, here majorly remind that according to valence bond theory, overlapping always takes place in between similar type of atomic orbitals only. Okay, and next, negative or in phase overlap. So here one orbital has positive charge and the other orbital has negative charge. So these two are overlapping, but these two are pz orbitals only, and these two are px orbitals only, and these two are py orbitals only, but signs are different. So that's why here we said that as negative overlap. And next one is zero or out phase overlap. So here, see in this first overlap, here S and P orbital. But S orbital is always spherical in shape, in that there is no explanation. Now concentrate on P orbital. So here this P orbital is um, in vertical position. Okay, so that is not arranged in straight position. So therefore, when for px and py orbitals, always we know that px and py orbitals are arranged vertically. So therefore, these are not overlapped with s orbital. Just pz orbital only overlapped with s orbital. That is only the possible overlapping. So this is not possible overlapping. And here also, see that px, py orbitals are not overlapped with each other. Px is again overlapped with px only, py is overlapped with py only. But here they indicated that px and py. So these two are different orbitals, no? So that's why this overlapping is not possible. Therefore, zero or out phase overlapping means these are not possible. And next, bond parameters. So here bond parameters are important topics only. So that are bond length, bond angle, bond energy. Bond length, bond angle, bond energy. So first bond length. Bond length is what? It is the average distance between the nucleus of two atoms. Suppose here if two atoms are comes to close each other, like this. If two atoms are comes to close each other, then the average distance is called as bond length. Okay, so therefore here it is the average distance between the nucleus of two atoms. Its unit is angstrom. So what is the unit of bond length? Unit of bond length is angstrom. Now it depends on electronegativity of constituent atoms. It depends on electronegativity of constituent, means which atoms are comes to close each other. Those atoms are said to be constituent atoms. Now if electronegativity difference is 0 for AB molecule. Okay. So here I am explaining about AB molecule. These two, in AB molecule, A and B are constituent atoms. Okay. So if the electronegativity difference between these two atoms is 0, then the distance between AB molecule is always equal to radius of A atom and radius of B atom. Therefore, distance of AB molecule is equal to radius of A plus radius of B atom. If electronegativity difference is not equal to 0, here condition is if electronegativity difference is not equal to 0, then the distance between AB molecule is Ra plus Rb minus 0.09 into Xa minus Xb. Okay. By knowing Xa minus Xb value, we will find out the distance. So here electronegativity difference is not equal. So that's why compulsory they mention that Xa minus Xb value. With Xa minus Xb value, we will find out the distance of AB molecule. Okay. So here remind this formula as distance of bond length of AB molecule is equal to Ra plus Rb minus 0.09 into Xa minus Xb. Now, here which factors affect the bond length? So, these factors are very important. Okay, with these factors only, we will say that for which molecule bond length is more, for which molecule bond length is less. In that, the first factor is that electronegativity difference. Electronegativity difference. See here, bond length is indirectly related to electronegativity difference. Means what? On increasing electronegativity difference, bond length decreases. Bond length is decreasing. So that will be explained with example. Now here I took 4 molecules HF, HCl, HBr, HI. So generally electronegativity of fluorine atom is 4 and hydrogen is 2. Okay, so therefore here the difference will be 2. In the same way, electronegativity of iodine is 2.5 and hydrogen is 2. No? Now here the difference is 0.5 only. The difference is 0.5 only. Means on increasing electronegativity difference. So electronegativity difference is more in hydrogen fluoride. More in hydrogen fluoride. So therefore, the bond length is more for hydrogen iodide. These are inversely related with each other. See here. I given the electronegativity values also. So therefore, the electronegativity difference is more in HF. Therefore, its bond length is less. Okay. So that's why this is one of the factor. This is one of the factor. So like this, here bond length is explained. Now, the second factor is the bond order. Second factor is the bond order. So what is the bond order? Bond order is meant by number of bonds in between two atoms. Okay. In between two atoms, the number of bonds only called as bond order. Now, how it related? Bond length is indirectly related with bond order. Okay. So now see with the examples. So here I took the three types of molecules. In first molecule, single bond is present and double bond is present, triple bond is present. So means what? The bond order is here 1 and 2 and 3. The number of bonds only, no? So bond orders are 1, 2, 3. On increasing bond orders, bond length values are decreased. Okay. So here 1.54, 1.34, 1.20. And see other example. Here I took that carbon and nitrogen atoms. In first molecule, single bond is there, double bond is there, triple bond is there. So its bond order is 1 and its bond order is 2 and its bond order is 3. On increasing their bond orders, bond lengths are decreasing. Okay. So therefore, bond length is indirectly related to bond order. Now, next factor, resonance. Resonance also affect the bond length. Okay. How it affect? I will explain with example. Generally, see the example, that is benzene. Benzene has two resonance structures. Okay. In these resonance structures, just you observe, in between two carbon atoms, single bond as well as double bonds are present. Okay. So, in between these two carbons, single bond, and next to two carbons, double bonds are present, and next to carbons, single bonds are present. So, finally, in resonance structures of benzene, single bond and double bonds are present. Okay. But the bond length in between two carbons in resonance structures of benzene is equal to 1.39 angstrom only. This bond length is not equal to single bonded carbons of bond length and double bonded carbons of bond length. So that is in between of these two values. Therefore, that was affected by majorly resonance. And next bond parameter, that is bond angle. It is the angle between any two adjacent bonds. Now, which factors affect the bond angle? Okay. So, suppose if molecules are arranged, like atoms are arranged like this, then the bond length will be explained in this way. Okay. If that are arranged, then the bond angle is explained in this way. If that are arranged in this way, then the bond angle will be takes place in this way. Okay. So therefore, it is the angle between any two adjacent bonds. Now, which factors affect the bond angle? So first one is number of bonds. Number of bonds are nothing but bond order. Now, bond angle is directly related to bond order. See that Here single bonds are present. No? So therefore its bond angle is 109 degrees, 120 degrees, 180 degrees. Okay. So on increasing number of bonds, bond angle increases. Bond angle increases. Okay. And next factor, hybridization. So hybridization purpose, here different explanations are there. So all these are important. Compulsory, objective wise, these are important questions. Now see that bond angle inversely related to number of lone pairs on the central atom. Okay. Now see here conditions are hybridization and bonded atoms are same. Central atom and lone pair are different. Okay. So bond angle is inversely related to number of lone pairs. On the central atom, number of lone pairs on the central atom. Okay. So now with example I will explain. Here I took the three types of molecule: methane, ammonia, water. In all these molecules, which hybridization takes place? sp3 hybridization takes place. Okay. So therefore, bond angle in methane molecule is 109 degrees, ammonia is 107 degrees, and water is 105 degrees. So here, what you observe, the central atom is different. Okay, na? Sorry, central atom is different with different central atoms. Okay, so with different central atom and different lone pairs, the bond angle is affected. So how it affects? On increasing lone pairs on the central atom, more repulsions occurred. Due to that repulsions only, this bond angle decreases. Okay, so due to more inter-electronic repulsions, bond angle decreases. Now see, in all these molecules, which hybridization takes place? sp3. Now see the conditions. Hybridization is same. Okay. Bonded atoms are same. So what are the bonded atoms? Hydrogens only. Bonded atoms means sidewise atoms. So which are different? Central atom is different. Okay. And lone pairs are different. Here there are no lone pairs. One lone pair and two lone pairs. Okay. And next, second point. Bond angle directly proportional to electronegativity of central atom only. Okay. So now see the conditions. Here hybridization, sidewise atoms and lone pairs are same. Okay. But which are different? Central atom only differing. Okay. So therefore bond angle is directly proportional to electronegativity of central atom. Now see the example. In this example, I took the three molecules. One is ammonia, phosphine, arsine. In these three molecules, which hybridization takes place? sp3. Hybridization is sp3. So therefore, here I said that hybridization is same. And next, bonded atoms are same. Sidewise atoms are hydrogens only. And lone pairs are same. So lone pairs are one only. Okay. But central atom is different. Here nitrogen, phosphorus, arsine. So now by decreasing electronegativity of central atom, bond angle decreases. So we know that electronegativity of nitrogen is more than phosphorus than arsenic. So therefore, along with that, bond angles are decreases. And next factor, bond angle is directly proportional to size of side atom, indirectly proportional to electronegativity of bonded atom. So see here, 2 points I given. For this, see the conditions. Hybridization, lone pairs and central atom is same. Okay, hybridization is same, lone pairs are same and central atom is same. Bonded atoms, sidewise atoms only different. When sidewise atoms are different, here sidewise atoms are fluorine, chlorine, bromine. Okay, with fluorine, chlorine, bromine. So bond angle is directly related to size of side atom. So generally from fluorine to bromine, atomic size increases. No? In this way, the bond angle also increased. The bond angle also increased. See that. Here 105 degrees, here 111 degrees, and here 180 degrees. And one more point is that it is inversely related to electronegativity of sidewise atoms. Okay. So electronegativity of fluorine is more than chlorine than bromine. Therefore bond angle is increasing. Okay. So means here the point is when hybridization, lone pair and central atom are same, then the bond angle is differed with different bonded atoms. So bond angle is directly related to size of sidewise atoms and indirectly related to electronegativity of bonded atoms. Okay. So next factor, bond angle is directly proportional to S character. S character. Okay. So here I took that three molecules, beryllium chloride, boron trichloride, carbon tetrachloride. In beryllium chloride, sp hybridization. In boron trichloride, sp2 hybridization. In carbon tetrachloride, sp3 hybridization takes place. Okay. So S character is more in sp hybridized orbitals. That is 50-50%. No? So therefore the bond angle is more here. And next bond angle is more in sp2 hybridized orbitals of compounds. And next sp3. So here on increasing percent of S character. Percent of S character is increasing from sp3 to sp2 to sp. Bond angle increases from 109 degrees to 120 degrees to 180 degrees. Okay. And next bond parameter is bond energy. It may be defined in two ways. One is bond formation energy and other one is bond dissociation energy. So here bond formation energy, bond dissociation energy, both are similar. But definition purpose little bit difference is there. It is the releasing energy. Already I said initially. Whenever a bond is formed in between two atoms, energy is released. Okay. So therefore, it is the releasing energy for the formation of a bond. And oppositely, it is the required energy for the dissociation, deviation of a bond. Okay. For deviation, energy is required. For formation, energy is releases. That energy only called as bond energy. Okay. So these two are related to bond energy only, but that will be defined in two different ways. Now, next, which factors affect the bond energy? Here's some more points are there. First point, electronegativity difference. Bond energy is directly related to electronegativity difference. Means on increasing electronegativity difference, bond energy increases. So how? On increasing electronegativity difference, attraction increases, no? Along with that increased attraction, bond energy increases. Therefore, HF bond energy is more for HCl than HBr than HL. And next, bond order. Bond order means number of bonds. So that bond energy always directly related to bond order. Okay. On increasing number of bonds, bond energy increases. And next, atomic size. Bond energy inversely related to atomic size. Inversely related to atomic size. See here. Here I took that three types of bonds. Okay. So one is bonds are present in between two carbons, bonds are present in between carbon, nitrogen, and the other one is in between two nitrogen atoms. Okay. So generally from left to right, in any period, atomic size decreases. Okay. So in this way, bond energy increases. Bond energy increases. So from carbon to nitrogen, carbon, nitrogen. Atomic size is decreased, no? Therefore, bond energy increased. Means attraction is increases due to decreasing small size. Therefore, bond energy increases. But here exception case is there. So what is that? In halogens, chlorine, bromine, fluorine, iodine. Okay. So these all are the 17th group of molecules. In all these, actually the bond energy will be more for fluorine molecule. But its place is changed from here to here. So why? Due to more inter-electronic repulsions in fluorine molecule. Due to more inter-electronic repulsions in fluorine molecule, its bond energy is decreased. Okay. So actually it has small size, and again when more inter-electronic repulsions are occurred, in all these three lone pairs are present, but due to having small size, more inter-electronic repulsions occur. Okay. So therefore its bond energy or bond dissociation energy is decreased. Therefore its place is changed from here to here. And next, in same reason, in the case of oxygen and sulfur. And next point is that bond polarity. Bond polarity. Polarity means attraction only. Bond energy directly related to bond polarity. Okay. So that bond polarity is more. Therefore bond energy is more. And next, S character. So bond energy directly proportional to S character. Okay. So here S character is more in sp hybridized orbitals. No? So therefore the bond energy is more than sp2 than sp3. And next factor, lone pair of electrons. Lone pair of electrons. Bond energy inversely related to lone pairs. Okay. So see this example. In carbon, there are no lone pairs. In nitrogen, one lone pair, and oxygen, two lone pairs, and fluorine, three lone pairs are present. On increasing lone pairs, electronic repulsions increases. Therefore, bond energy decreases. Okay. So here more repulsions occurred in fluorine molecule. Therefore, its bond energy is completely less compared to other molecules. Okay. So these are about bond energy. I think you followed this class. Okay.